Hi, I'm Laurie. We're going to continue going through photon beam characteristics. This time we're going to talk about attenuation and scatter. So in the first video, I went through inverse square law. This is the second video. There's also a quiz associated with this at the end to help you consolidate your knowledge. Attenuation. So attenuation decays exponentially according to the Beer-Lambert law. That is, that the intensity at depth d, when you change the depth, but you keep at the same distance from the radiation source, so just like adding bolus but not changing the distance of the point of interest from the source. So, like I said, the transmitted intensity at depth d is related to the intensity at depth 0 multiplied by the exponential of minus e to the minus mu d. So what the linear attenuation coefficient is mu. This is in units inverse centimeter. A good trick to know is that logarithms and exponentials have to be unitless. So the exponent here, mu d, must be unitless. We know the units of d are centimeter, so units of mu must be inverse centimeter. Some assumptions that there's narrow beam geometry, which means we're not counting scattered photons in the transmitted portion. So the transmission fraction is after both absorption and scattering processes. So this is what you would measure if you had an infinitesimally narrow detector. You would only detect the direct unscattered beam. We're also assuming monochromatic or monoenergetic. This is because mu is only constant for monochromatic cases. It's polychromatic, it has different values, different energies, you have to do the integral. So the linear attenuation coefficient is related to the transmission fraction. That is the fraction of photons removed from primary beam by absorption and photon scatter. These, it does not, the transmission fraction and mu don't give the energy absorbed. That need mu en over rho. I'm not going to discuss mu en over rho here, but it's useful for other aspects of radiation therapy. This is just a refresher. I'm just going to give this, I'm not going to go through this slide. This is just information for you. For example, it's good to know that the e to the minus infinity is 0. So if you have e to the minus a large number, it's going to be a very small number. So half-value layer, a very important concept. This is the thickness that reduces the intensity by half. So mathematically, I over I0 is 0.5 to the power n, where n is the number of half-value layers. It's linear in a semi-log plot. You can rearrange this. So the number of half-value layers is the natural log of transmission divided by 0.693. So then you can ask the question, what's the transmission for 5 half-value layers? So then it would be 0.5 to the power 5, so 1 over 2 to the power 5, so 2, 4, 8, 16, 32, 1 over 32 is your answer, so about 3%. So HVL and mu are related also by this logarithm of 2, so half-value layer multiplied by mu is 0.693. A really easy way to remember this is if you're given one or the other, so if you're given the HVL, you just do 0.693 divided by the HVL, gives you mu. If you're given the other one, it's the same formula, so if you're given mu, it's 0.693 divided by mu is the HVL. It's just, I went through that. Mean free path is just 1 over mu, or 1.44 times the HVL. It's the average distance between interactions. So a little HVL example. Yeah, there are some useful NIST web pages given here. And you can ask the question, what's the HV of water? Just get a rough idea. 6 MV, so just approximate as 2 MeV monoenergetic photons. So the NIST websites, they give tabulated data like this. Luckily, the rho of water is 1, so mu of a rho, we just multiply by 1 to get mu. We don't need to know much about mu en of a rho right now. So we're just concerned with the linear attenuation coefficient. So 0.693 from the previous slide divided by 0.0494 is from this table. It's 14 cm. So that's roughly how much water you need to reduce the attenuate 6 MV beam by half. So just to give you sort of a rough idea of the sort of length scales we're dealing with. So water 14, bone about half that, titanium about half that again, lead quite a lot lower. And these are obviously much longer than in the KV region. We have much shorter attenuation, half value layers. Just one quick point is that in the KV region, for most CT scans, we can't really tell the difference between most metals. Basically, everything above 3 or 4 grams per centimeter cubed, they're all more or less opaque to the CT scanner. So a lot of metals look the same, even though they're quite different in density. So titanium's only 4 grams per cc, lead's 11 grams per cc. It has quite different half-value layers in the megavoltage regime. So it's okay to treat through titanium, for example. It's not okay to treat through lead. The CT scanner might not necessarily distinguish that for you. So you do. Okay, so that's attenuation. So now scatter. Scatter is the smallest of the big three. So we've gone through distance, inverse square law, attenuation, Beer-Lambert law, and half-value layers. Scatter is the third effect, and that is that the scatter conditions change when we change field size. Right, okay, so a point to note about field size definition. So obviously we have diverging sources, so the field size depends on distance from the source. But actually the machine settings, the field size given is usually defined at 100 centimeter or the isocenter distance. It's a good thing to know. So for example, 10 by 10 is only 10 by 10 at 100 centimeters. So we're talking about field size because phantom scatter depends on field size. So scatter can be broken down into 2 components mainly. Phantom scatter, so when we have small field size, we don't have much phantom scatter. The dose at point A here is mainly from the direct beam and only the direct beam. When you increase the field size, there's additional dose adds up to point A from scattering from the other regions of the radiated field. And as you change the field size, then you change the amount of scatter that reaches A. And so the scatter that originates in the phantom of the patient from surrounding areas, that's called phantom scatter. Collimator scatter is a little bit more tricky. So collimator scatter is from the collimators, primarily the jaws in the varying machines. And the effect, although some of it reaches the patient, most of the collimator scatter is actually affecting the monitor chambers. So it's changing the ratio of the dose at the reference point in the patient compared to the charge measured by the monitor chambers. And it's doing that mainly through backscattered dose from the jaws. And what you really need to know is that it's always increasing with field size. Both effects increase with field size. So larger field sizes mean more scatter in the patient. A few key points. Phantom scatter is scatter in the patient. It depends on the size of the radiated volume, so the size of the volume radiated at the patient. We cannot measure phantom scatter on its own because we always have a collimator. We can, collimator scatter, however, is scatter from the collimators, and most of it is from the collimators into the monitor chamber. It depends on the field size at the jaws, so not so much the field size on the patient, the field size at the jaws. So if you have some tertiary collimation, such as an MLC, it's mainly dependent on the field size at the jaw. Collimator scatter can be measured on its own by measuring in air, and the combined factor is called S sub C P. This can also be measured in a phantom. You can see it varies about 7% from small field sizes to large field sizes, and it is equal to 1 at the 10 by 10 reference field size. By definition, at calibration conditions, it's the same. The dose here is the same as it is at calibration conditions when the field size is the same as the calibration conditions. So I said we can measure collimator scatter in air. So if we don't have a phantom, we just put a detector in air, take the ratio of the measurements of different field sizes, we can measure the collimator scatter factor. And then the combined scatter factor we can measure in a water phantom. So when we're at the same SSD as the calibration, same depth as the calibration, we just vary the field size, we get the ratio of the dose at any given field size compared to that in the calibration conditions. So that's it on scatter. Please use this quiz to consolidate your knowledge. I'm also going to show some similar questions on the next slide. You can just pause the video if you want to answer these questions. That's it. Thanks.